Convection. Convective heat transfer, when we are talking about, so it is actually bulk movement of molecules within fluids such as gases and liquids. So, when we are talking about convection, so it is not solid, it is gas or liquid. Okay. So, how it is working? Like say I have one flat plate. Okay. This is my flat plate and fluid is flowing over it. It is creating one boundary layer, as you know already in fluid dynamics. Okay, and my inlet flow velocities are like this. Okay, equal flow velocity you are giving, but whenever it is going over the flat plate, so near wall, let's say this is my wall and fluid is flowing over it. So near wall, fluid particle will not be able to moving with the upper layer. Okay, because near no slip condition, we say no slip condition means near surface fluid will be having very low velocity because of friction. Okay, so that's why this fluid particle will be low friction fluid velocity, but if you go a little bit up, little bit higher fluid velocity will be there, then further higher fluid velocity, further higher fluid velocity. So I will get one curve. Okay, and this is called u infinity or actual velocity of whatever u velocity you have given, that velocity. But near wall or solid body, the velocity will be lower because of the friction. Fluid will have low velocity. Okay, that's why you will have that gradient. Okay, and this line is delta. Okay, this is called boundary layer thickness. Boundary layer thickness. Okay. So when fluid is entering, the boundary layer thickness will be very small, but after certain time it will be very higher. Then after certain time, boundary layer can be broken. Okay, so that I am not drawing here. This is u velocity. This is I can draw. This is y. This is x. Okay. Then uy velocity. So uy velocity going. Okay. Then this is y actually. So my velocity, how it is changing, we'll see this. Okay, as I am moving from left end to right end, fluid velocity increasing and distance from the layer, the delta, the distance is increasing also. Okay, but in what is happening, like if it is heated, like say T surface temperature is higher, and it's 100 degrees centigrade, and air temperature 20 degrees centigrade, that means from surface heat will be transferred to air, because air temperature lower, surface temperature higher, the temperature gradient is created. Then how this temperature profile look like? So temperature profile will look like this. Okay, and temperature profile we have another boundary layer. This is thermal boundary layer. Okay, so I can draw like this. Okay, so this is delta T, this is thermal boundary layer, thermal boundary layer BL, I am writing BL. Okay, so this is thermal boundary layer. Okay, this one, this is thermal gradient. Okay, this is for thermal, this is for velocity. Okay, so you can see thermal boundary layer near wall, it is right side. What is happening? Particle are not moving near wall, so temperature. Okay, so particle are not moving near wall, so temperature is higher. So if you go away from wall, like say wall is here and you are moving up, so temperature is higher, temperature lower. But if you draw that one properly, so it will be coming like this. Okay, you see this one thick line I have drawn. This is thermal boundary layer it is creating. Okay, this is gradient is created within this boundary layer, and upper portion is going to u infinity or T infinity. Okay, and for convective heat transfer, formula is Q equals HA del T. H is called convective heat transfer coefficient. Okay, and this is coming from Newton's law of cooling. So fluid is heated, thermal expansion of lower layer due to heat. Okay, so near wall, thermal expansion will be happening. Okay, then buoyancy will be working. Buoyancy will be working means, like I have one plate and one particle is here, two particle, three particle, many particles are there, and near wall this will be expanded because it will take heat and it will be lightweight because it is expanded already, it will move up. Okay. Then what will happen, other cold fluid will try to take this space. Again this cold fluid will take heat, it will be expanded, and because of buoyancy, when it is expanded, its actual weight is reduced. Okay, average weight is reduced. So then other heavier particle will try to take this space, it will move up, and when it is coming to the heated area, again it will be expanding, again it will try to move up, another cold fluid will be coming. So that way this cycle will go on. Okay, so buoyancy will be working. Okay, because of buoyancy, expansion will be happening. Near wall, this is heated wall, this is cold particle. Okay, so cold particle will come, it will get heated up, move up, again cold particle come, heated up, move up. So that way this whole cycle will go on. Okay, so colder and denser fluid replace the expanded particle, you can see. Natural convection. Okay, so if there is no air blowing over it, let's say I have taken one cup of tea. Okay, and there is no air blowing, so this will take longer time to be cooled. Okay, but if I have one table fan here. Okay, table fan here, and it is blowing air at very high rate, then cooling rate will be very high, so quickly it will be cooled. So this is called forced cooling or forced convection. Okay, so natural convection means particle will be heated up slowly, low density particle or expanded particle will move up, again cold particle will come, again it will get heat, it will move up. So the rate is slow, heat taking from the water surface or my tea or coffee will very slowly it will be happening. Okay, this is called natural convection, this is slow process. But forced convection, when air is blowing over it, so some let's say one particle got heated up and air will be forcing this to move away from the cup. Okay, in previous case what was happening, air got heated up, one particle, so particle because of buoyancy slowly it will move up. Okay, but when you have one fan, so it will not go slowly up, rather because of air blast or air blow, this particle will be forced to move away. So when forced to move away, another cold particle will be taking that space, it will take certain amount of heat, again it will be moved away, again another cold particle. So cold particle coming and T temperature already higher, so cold and higher temperature, the temperature gradient is higher, means heat transfer rate to the particle will be higher. When cold particle is getting quickly heated and quickly removed, again another cold particle coming, quickly heated, quickly removed, so that will be increasing your heat transfer rate. So whenever you have forced convection, your heat transfer rate will be higher. When you have natural convection, heat transfer rate will be lower. Another term is used actually, mixed convection. Mixed convection heat transfer. Okay, mixed convection heat transfer, what happens? Natural convection means there is no air blow, slowly particle moving. Forced convection, you are forcing particle to go almost horizontal direction, move away from my water surface or tea surface or coffee surface. Now mixed convection means your air blast is not so high that particle will be going horizontally, rather it will be one particle is trying to go up, natural convection. Forced convection is going horizontal, almost horizontal. Mixed convection will be like it will make certain angle, so heat transfer rate will be in between natural and forced convection. Okay, and H or convective heat transfer rate, so natural convection convective heat transfer rate will be lower, H will be lower, and forced convection H will be higher. Okay, so H will be depending on density, viscosity, thermal conductivity, specific heat capacity. Okay, it is not a material property, it is actually fluid property. Okay, whether fluid is having certain very high thermal conductivity or forced convection, natural convection things are there, then its H value will be increasing or decreasing. One simple thing, the rural chula or oven people uses for cooking purpose, you can see in rural areas, right? They will put water or food, and there will be one hole for fuel, or like say wood will be inserted through this one, and fire will be here. Okay, here lots of science is there actually. If you see this chula system, okay, why I am saying lots of science is there. So wood you are putting and lots of space is here. So wood plus air actually you are giving through this one, okay. And hot gas, when it is burned, when air is hot, so the particle will be expanded particle will go up, okay, it will try to go up. When it is going up, this hot, your pot or vessel, it will be touching this surface, okay, it will be transferring heat to this pot, okay. The hot gas is going out, it will be touching the pot, it will be transferring heat to the pot, okay. Then inside pot, water will get convective heat transfer, okay. Pot will be heated up because of conduction, heat will be transferred through pot to the water, and inside water there will be lots of convection will happening. Convection means one hot particle will move up, cold particle will be going down, so that way it will be creating a turbulence in environment inside, and whole water will be heated up. After a certain time, this water will be starting boiling, okay. So how heat is going? Initially it will be going through radiation and convection. Hot particle will be touching here, and radiation means no medium will be required, directly from fire heat will be touching this pot, okay. So the pot will be getting heat using through radiation mechanism and convection mechanism, and some conduction also possible. When this oven will be heated up, you see these two point is connected, so the heated up portion also will be transferring heat to your metal pot. And the normally pot will be metal. Previous days, older days, it was earthen pot also were there, but this is metal pot will be there. Metal will be having very high conductivity. Aluminum pot and iron, stainless steel also people are using. Sometimes cast iron also people are using. So those will be having higher heat conductivity. So the water will be, or your food will be boiled accordingly. Okay, so you are using conduction, convection, radiation, all the mechanism through this one. People were using thousands and thousands of years ago, they designed it, but they never thought about this science and mathematics is there in between. Okay. So whenever you are talking about heat conduction or convection, especially convection, so you have to remember the term Reynolds number. Okay, mu L by U L by mu. Okay, not mu, nu. Okay, U means fluid velocity, and is the characteristic length, and this is viscosity. Okay, so this is inertia force by viscous force, inertia by viscous. Okay, so if Reynolds number is very high, that means fluid velocity is very high. When fluid velocity very high, hot particle would be moved quickly, again cold particle coming, move quickly. So high heat Reynolds number means high heat transfer rate actually. Okay, and another term will be coming Nusselt number. Nusselt number, the ratio, I'll write here, Nusselt number. Many other numbers also there, these are called non-dimensional number, Reynolds number, Nusselt number, Grashof number, Pentel number. So many numbers are there used in heat transfer cases. So one term is called Nusselt number. Nusselt number is the ratio of convective to conductive heat transfer at a boundary in a fluid. Okay, so HL by K, the formula. Now another term is there, Prandtl number. I'll write here, Prandtl number. Prandtle number. Prandtl number, the ratio, this also ratio of the dominance of velocity or hydrodynamic boundary layer, or hydrodynamic boundary layer. The formula is nu by alpha equals mu by rho K by rho Cp. Okay, nu is kinematic viscosity, dynamic viscosity divided by rho, and K thermal conductivity, rho density, Cp specific heat. Okay, so K is thermal conductivity, rho density already you know, alpha is K by rho Cp. So K already you know, then rho density Cp. Okay. So momentum diffusivity by thermal diffusivity. It's called momentum diffusivity by thermal diffusivity. Okay. So in free convection, the gas convective heat transfer coefficient 2 to 225 watt per meter square K, liquid 50 to 100. Forced convection, if you see, it is increased actually. Okay, it is 2 to 25, it is 25 to 250, so a huge amount of increased. Liquid, you see, so much increased. Boiling and condensation, when it is happening, H value 2500 to 1 lakh also possible, 100,000. Based on that, we will solve one problem like area 100 feet square. Let's say this area is 100 feet. Okay, this body is having 100 feet area, and H value is given 20 British thermal, not BUT, BTU per hour feet square per F. This is Fahrenheit. So normally we are in India, we use SI unit, but if you are working for oil and gas industry or many marine engineering application also, they will be using BTU unit, okay, British thermal unit. So whenever you are solving any problem, you have to check whether it is BTU or it is what kilowatt is given. Okay, so you do not mix up the unit. If you are mixing up, then there will be error in your calculation. And surface temperature is given 280 degree centigrade, 280 degree Fahrenheit. Okay, and T air temperature is given 80 degree Fahrenheit. So simple heat transfer formula is that H A del T. Okay, so H is given your 20, A is given 100, and T is given 280 minus 80. So it is coming 400,000 BTU per hour. Okay, so here it is given hour, so it is coming hour actually. So if it is given minute, then you have it will come minute. So you can check with your unit also. Okay, when you are balancing units, how much, what is this unit and what unit you are getting for HT. So that if you check properly, then you will get proper value.